Okay, Assalamualaikum warahmatullahi wabarakatuh. We're going to continue with the solid state control of the DC drive. Okay, so we have talked about the three methods of controlling the DC motor based on the resistance control. Then we have this armature voltage control, and the third one, which is the field control. Is it? And now we look into how we're going to change or how we're going to control the armature voltage control by means of using the solid state control. We have discussed on uh, the first few slides, which is we define what is a base speed and what is a field weakening, isn't it? And then we look into the two types of, which is the control rectifier type, whereby the input side is the AC supply, and then you're going to control the motor. And then we also going to discuss on, we're going to look into how, if we have the input is DC, and then we're going to control straight the DC motor. So we're going to have a control rectifier fed drive, and the second type will be the DC-DC converter fed drives. So just ignore this AC supply. So we talk about the input is a DC, and we're going to control the motor, DC motor. And then we also look into this 4-quadrant operation. I'm going to repeat it again and again, because this is a key the fundamentals. You need to understand the 4-quadrant operation before you can really look into how to control the speed of the motor. Okay, so this will give you the condition of your motor as well as your load, right? So there are, of course, 4 quadrant. The fundamental, or the standards characteristic of the axis that we're going to use is omega on the y-axis, and we have torque on the x-axis, and that will give you the quadrant 1, quadrant 2, quadrant 3, quadrant 4. And if you change the axis such that we have a torque versus speed, then the quadrant always follow the sequence Q1, and then you have Q2 here, then we have Q3, which is the same as the one previous one, and the Q4 will be there, which is the opposite of that, isn't it? Okay, so we always have use this omega versus torque, or sometime later on we're going to use a V against current, the voltage of the terminal or armature, and then against the armature current, right? That will be the same quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay, so always look into this 4-quadrant operation. Look for the video on what is a 4-quadrant operation, and inshallah you will be able to understand this DC drive speed control easily. Okay, and then we start with the separate sighted DC motor, and then we look into the basic equation, right? Torque always K multiplied by, this is the well-known equation, torque equals to K flux IA, right? Or we're going to have E equals to, I'm going to write this, E equals to the same K, same K, depends on, sometimes KT, KV, but you have to understand that this constant K flux omega, right? So this is the same K here, so if you put T there, this should be also T, right? And then we also can break down that flux also can actually depends on is directly proportional to the IF, the field current. And therefore, if you want to make an equation, then that should be another KIF there, isn't it? Another constant there. And therefore, you can rewrite the torque equation here to be torque developed equals to the K T multiplied by K IF multiplied by IA. So you need to define a new K here. So there will be a new K. Let's say Kx, if you like, whatever K is, that will be a different K there. Get it? Right? So the key important thing is you need to memorize this equation. E equals to K flux omega, as well as T equals to K flux IA. So this is the two basic equation, two general equation that you need to memorize. Okay, and then we have this equation, torque equals to J. This is a mechanical. We have this J is the inertia of the motor, d omega over dt. This is plus B is the friction, omega plus load torque. So the torque developed by the machine equals to the torque of the load, as well as the friction and the inertia of the motor. Okay, then we'll look into the KVL, Kirchhoff voltage law of the circuits. Then we have this armature V equals to RA by. So this equation will define how you're going to control your omega. Okay, so I'm going to proceed. We start with the of the equation, and this is the schematic for gearbox. I'm going to look into the example of this while using the gearbox and the turn ratio. The gear ratio, the gear ratio as well, and we're going to look at that. Try to find the example for this, and I'm going to share with you. And this is a final gear. If you can refer the gear, the number of gear from the secondary to the primary side or primary to the secondary side, following the transformer, the transformer basic equation. So you can use that to apply in this motor. Okay, so we have looked into the rectifier, into the half wave drive, single phase half wave drive, and then we also look into the single phase full wave drive. Okay, this is the basic circuit, the half wave, whereby you have this this is a single phase, this is a single phase whereby the input is AC, and then you have this thyristor control, or sometimes we call it SCR, silicon control rectifier, right? And usually we use the thyristor, right? Thyristor here, and then you connect to the, this is a separately excited, separate, because your field winding is separate from the armature or the motor winding here. So this is separately excited motor. Okay, and we look at the solid state, and we also look into the first, which is a single phase half wave rectifier. Connect to your motor windings, and to simplify the analysis, we assume that it is a separately excited motor. Okay, so we connect the rectifier, the half wave rectifier, directly to the terminals here, and then this is the waveform. And if you look at the current in the circuit, they are discontinuous. Okay, remember, this is discontinuous condition, right? Because the current is discontinued. After some time you go to 0, then it rises again there. Okay, so the moment the current goes to 0, we have this beta, which is the extinction angle. This is extinction angle, and we have the discontinuous mode of operation, discontinuous current mode operation, when we have when sometimes the load could have the larger value of inductance. Okay, some of the heavy load, they have a very large inductance here, so your current is no longer discontinued, it will continue as a continuous current. So you're going to see that the current now is, so in that case you're going to have a different output voltage wave shape. Okay, you're going to have a different output voltage wave shape. Sorry for this. I'm going to have alternate. Okay, So we have a condition of discontinuous current mode, and to refresh, okay, how we get this output voltage waveform. Okay, so remember we start to trigger the thyristor at alpha, isn't it? At alpha. So before that, the thyristor here appear as a open circuit, isn't it? So when it is an open circuit, so there will be no current flow. There is no current flow. I equals to 0. So when there's no current flow, if you measure from that point to this point, which is the output, here we have this output Vt. Okay? So going to have, it will be equals to EA, isn't it? Because this is 0, there's no current, therefore there is no voltage drop here and there. Therefore, if you measure this point, these 2 points, Vt will be equals to EA, and that's why from 0 up to alpha, your output voltage equals to EA, the back EMF here. So when you start to trigger the thyristor, this will appear as a short circuit now. Okay, so I'm going to draw again. Here, after alpha, the firing angle, so your thyristor here will be replaced by a, a short circuit, right? So short circuit, so it is a current will flow. So there will be current flow. So look at this. This is the current developed in the circuit. So it will be a positive current I. So current start to flow. There will be a voltage drop here and there, and therefore, and if you measure from that point to that point again, the Vt, it will be equals to Vs, isn't it? Because you measure that point, so it will equals to Vs, and that's why at the output it will follow, after that alpha it will follow the Vs. This is your Vs, the sinusoidal waveform. So it will continue to follow the Vs until current goes to 0. So this is the point when current goes to 0 at beta, the extinction angle. So it actually exceed the 0 level here. So this is your 0 voltage, right? But still there is still current flow in that direction. The current still flow in that direction, even though the voltage is negative, reverse bias, but still we have current in the circuit. It force the thyristor to stays on, isn't it? And therefore, if you it will, the Vt here, the voltage across your terminal here will be equals to Vs again, until the current goes to 0 at that point. So when the current goes to 0, the cycle repeats. So open circuit, therefore Vt equals to EA again. So that's why you have the output voltage will be in this shape, isn't it? It goes there, and then it goes to that point. So this is the case of you have the discontinuous current. Later on, when we look into the full wave, we're going to look at how, if this current is continuous, the I here is continuous, right? So there is no longer beta, right? So beta is no longer exists, and we're going to have a different wave shape. Okay, so we're going to we have talked about this in the last video, so we're going to skip, and then and this is the voltage. I hope you go back and look into the Powertronic book notes from the previous semester, and this is the output voltage Vt, right? So this is Vt, and we have this equation here. So this is your EA plus RA, I average. So there's a equation there, right? And we have this conduction angle, right? The gamma here is the conduction angle, which is actually from alpha here until beta. So this is defined as conduction angle gamma. Look at that. So therefore, whatever beta is, you minus with alpha, it will give you the conduction angle or conduction period. Right, so you replace here to get all the uh, equation, and then you can find what is speed and the rest. Okay, so now we look into the single phase full wave. This is a single phase full wave drive whereby we have four diodes or four thyristors, and then we have this armature resistance, and also the armature circuits connected to the thyristor here. Normally we're going to draw like this, isn't it? I hope you still remember. The thyristor is always arranged in previous in the powertronics. Normally we draw the circuit uh, in this arrangement, isn't it? And then we have this R, L, then the back EMF here, and this is your supply into that. We have that into that, isn't it? So we have T S1, S2, S3, S4 there. Okay, so this is thyristor. Okay, 4 thyristors. So during positive half cycle, you're going to have S1 and S2 operates, and during negative half cycles, I'm referring to the supply voltage here. Okay, so during positive half cycle, this positive half cycle, S1 will operate as well as S2. Okay. When it is a negative half cycle, you're going to have S3 and S4 operate. Okay, so and current only flow in that direction. Okay, current will only flow in that direction. So therefore we have actually two quadrants operation. The previous half wave is actually one direction, one quadrant, and for the full wave we have two quadrant operation, right? And this is the case of, because a discontinuous current operation. Discontinuous current operation, whereby if you look at the current again, so it is discontinuous, so it will stop at that particular point. So similar with the previous explanation, whenever you have a current is zero, then there is no current flow, and therefore if I can may draw again, quickly draw that, then you have this, and this is your VT, isn't it? Your terminal voltage here, thyristor, and then your supply connected that point, okay, right. So whenever we have this current is discontinuous, which means there is no current flow, isn't it? So when there is no current flow, therefore if you measure VT, so VT will be equals to back EMF again, EA. Okay, will equals, because there is no voltage drop, there is no voltage drop here, so VT equals to EA. So that's what happens here. From there, this is alpha, isn't it? And you start to have this voltage, output voltage equals to the supply voltage until beta, right? Beyond beta, then current goes to zero, so it will equals to EA again. So this is your output voltage wave shape with the discontinuous current mode operation, isn't it? So what happens if you have a continuous current operation? Okay, which means your L here, your L is very large, especially for the heavy load operations. So look at that. For heavily loaded motors with high armature inductance, conduction period may equal or exceed 180%, which what does it mean is that your conduction angles here beyond 180%, 180 degree. So if you couldn't find where is your beta here, right? Because there's no beta, isn't it? There's no beta, and if you look at the angle, so here with a discontinuous operation, you still can measure gamma, isn't it? But if you talk about the continuous current, this is continuous current mode, and there is no beta axis. So what happens that there's no beta here, so you start to trigger that point, isn't it? Start to trigger the thyristor at that point, so voltage will follow that supply voltage, and there is no beta, so you keep continue to the thyristor continue to turn on, and then until it will saw the other firing angle for thyristor. This is for thyristor 3 and thyristor 4. So this is alpha for thyristor 1 and thyristor 2, and you will start to have the thyristor 3 and thyristor 4 180 degree plus alpha, isn't it? Okay. So therefore the output voltage will follow this wave shape, isn't it? So you will follow this wave shape, and you're going to have a different output voltage equation for Vt. So for Vt, it's simply 2 Vmax over pi cos alpha in the case of continuous operation. I can show you the simulation if you like. So if I go, if I can show you the simulation, in this case, let's assume we have this circuit, full wave rectifier. Let me show you. So this is supply voltage. Try again, try to use a PSIM to help you, to assist you in understanding the circuit operation, as well as the condition of current, continuous current mode, discontinuous current mode. So I'm going to show you how I simulate using the PSIM. So you have a supply voltage, right? So this is the parameter that you need to put in. RMS multiplied by square root 2, because you need to have this peak amplitude, isn't it? Rather than the RMS, so you have to multiply by square root 2. The frequency is 50 Hz, and then you have this special, what we call this as a one single phase thyristor bridge block diagram. Okay, so in here we have this single 4 thyristors. Okay, so there is 4 thyristors here, right? So there is a 4 thyristors here in one block diagram here, right? So it's already, and then the path for thyristor 1 is defined by this terminal, right? So you have this terminal. Okay, so this terminal actually requires the alpha. So how to provide that alpha? You need to use this you need to use this special alpha controller, they call it alpha controller. Frequency 50 Hz, pulse width. So pulse width is actually what is the width of your pulse. So if you define 2, which means this is 2 degree, so your pulse width will be 2 degree only. So it's very short pulse, isn't it? A short pulse through your circuit here, and the width is only 2 degree. You can also put 4 degree if you like, but normally you stick to a very low pulse, 2 or 4 degree, 2 or 4 degree if you like. You can use whatever it is, 2 to 4 degree, and very short pulse there. And then let me show again, what do we have here? And this is actually to detect where is this zero crossing, because this will be based on will actually be a reference of where alpha equals to 0, isn't it? Yes, so you need to tell the circuit here, alpha controller here, where is alpha equals to 0. So you have to sync or sense the supply voltage and then compare with 0. So this is a comparator, and let me show you. If I can click this is a comparator, right? You can look and find where is a comparator and elements, and the elements here, look for comparator. Okay, and then this is sensor. voltage sensor, gain is 1. So you don't have any you don't need to multiply or increase the gain, multiply or make it bigger voltage, right? So you just maintain at 1. And voltage sensor, so you sense the voltage, compare with a 0 level, 0, and then this will trigger the alpha controller here. Okay, so alpha controller, so that will tell where is 0 levels, and this is a voltage source to tell the alpha controller here what is the value of alpha, the degree, how many degrees. So it defined by this supply, this DC voltage, right? So if you put as a 30 degree, which means it is a 30 volt, so that equals to 30 degree. And you also need to put this pulse, okay, V step, right? Just look for where is a V step, and then we have 1 0, just maintain this value, right? 1 0 0.1 micro. So it will actually trigger, or it will actually turn on the alpha. So just put this call it V step here to activate, right? The term is activate the alpha controller here. And then next you have R L, okay, just use this value if you like. And then we have the back EMF, so it represented by back DC voltage to represent the motor. Yeah, so later on probably you may need to use the DC motor module or model put into that. This is just to show you the converter. Show you the converter. Okay, so here we have this operation LA. The inductance is 0.03, or probably I can start with 0.02 first, which is 1 2 3 20 millihenry. Okay, we start with 20 millihenry and look at the output waveform. If I run this mission, run, okay, okay, there you are. Right, look at the current. So the current is discontinuous, and we have this as alpha. So here is alpha, and there here we have pi plus alpha, which is this is times the 1 and 2, and that one is times the 3 and times the 4 operates alpha and alpha plus pi. And here we have this beta here, isn't it? So this is beta, where the current goes to 0 at that point. Okay, current goes to 0 here, and we have beta here, there. And look at the waveform. Right? So now we have a discontinuous operation. Okay, so however, when you deal with a large heavy load, and normally L is very large, so let's change to 0.3 or 0.5, 0.05, 50 millihenry. Run the circuit again. Now look at the current. Look at the current. It's no longer discontinuous. It is continuous. Look at that. There is no discontinuous. So the current is continuous. It always flow in the output, isn't it? So therefore, it will force the thyristor 1 and thyristor 2 to stay on until you trigger thyristor. So this is the area where we have thyristor 2 and 1 operates, and this is 0 crossing. So thyristor 1 and thyristor 2 will experience negative or reverse bias, but due to the current still flowing in the output, and it will force the thyristor 1 and thyristor 2 to stay on until you trigger thyristor 3 and thyristor 4. Okay, at pi plus alpha. So here you have alpha here. Okay, and that's why you have a different output voltage now in the case of continuous current mode. Okay, continuous current mode operation. Right, so that to show you, to explain to you what is a discontinuous and continuous current mode. Right? Okay, And therefore, let me show you again, as we have, and the output equation equals to 2v max over pi cos alpha. Okay, so in that case, when we have a um, we call it continuous current mode operation, your output voltage can be positive and sometimes it can be negative, which means the polarity will change, isn't it? So here, if you look at the notes here, it says that if you alpha is in between 0 to 90 degree, you're going to have a positive VDC, which is positive VT here. But in the case of, if you go beyond 90 degree, 90 to 180 degree, your output voltage now will be changed. I mean, the polarity will be changed. It's no longer positive negative, but it will be negative positive here. Right? So in this case, and the current still flowing in that direction, isn't it? So the current still flowing in that direction, IA, and therefore you are actually operate at so we have omega and torque and that also can be represented by voltage again, current, isn't it? Voltage again current IA. Okay, so when you have your current still positive flowing in that direction, so it's positive, but your voltage can be positive and negative. So you operate in these two quadrants, which is Q1 and Q4, right? So you have Q1 and Q4, which is we have a positive voltage here, and after if you operate beyond 90 to 180 degree, you're going to have negative voltage operation. Okay, so by changing the value of alpha, you can have two modes of two quadrants operation, which is Q1 and Q4. Okay, so how are we going to change that or increase that or improve that motor to be operate in the whole for the whole quadrants here, Q1, Q2, Q3, Q4. So that comes dual converter solution. So you're going to have dual converter operation. Dual converter operation. So when you have a dual converter operation, you're going to have the same circuit here, but connected in anti-parallel connection. Right? Converter 1, converter 2, but the converter 2 now will be inverse parallel. I mean, it is anti-parallel, which is connected in anti-phase. So you're going to have a different direction of thyristor, that direction. So here, you're going to have that your converter 1 will operate when the current start flow in that direction, but converter 2 will operate in that direction. Okay, so single phase, and again phase control for quadrant Q1, Q2, Q3, Q4. So quadrant 1 and quadrant 4 only operates with by using this converter 1 here, and quadrant 2 will control Q2 and Q3. So again, condition for 4 quadrants, and please memorize this, right? So you have a speed, again torque, or you can also have voltage. Here it puts a VA, so don't worry about the notation. Sometimes it's known as a VT, sometimes it's referred to as a VA. So that is the terminal voltage, and then we have current here, right? So this is current, IA, the armature current. Okay, so look at the current direction is positive, flowing that direction, and then we have positive VA, and you're going to have to see the same back EMF polarity here. So for forward motoring, VA should be greater than EG. Why? Because you want the current to flow in that direction, isn't it? So VA must greater than EG. Okay, So in the case of second quadrant, the current is reverse. So how to make the current reverse? Going to let EG, which is the back EMF, is greater than the terminal voltage. Then you can have this condition IA. In this case, you're going to have a forward braking. Here is known as a forward motoring. Q2 is known as a forward braking. So the current reverse because EG greater than VA. So that's why current flow in that direction. But still we have a positive VT rate. Okay, and then the rest, I hope you can understand. This is the reverse motoring. Right? So reverse motoring, whereby the current is reversed, and you also have a different polarity of the voltage. So if you still remember, normally if you have you're going to have a counterclockwise direction for omega, you have a positive speed. But now if you refer to that, you're going to have this. That will be your omega. Is that it? And the torque also in that direction. Torque develop or torque electrical torque or developed torque, TD or TE, in that direction. Is that it? So this is known as reverse motoring, whereby your current is, your voltage is negative and your current also in the negative direction. So this is only can be handled by the second, can be handled by your second converter here, isn't it? Because current flow in that direction. Okay, current flow in that direction. So converter 2 will operate in that quadrant 2 and quadrant 3. Okay, right. So go further. If converter 1 operates with a delay angle of alpha 1, then you have the armature voltage is, this is from the previous continuous current mode operation. So VA equals to 2 V peak over pi cos alpha 1, and alpha only can be from 0 to pi. VM also known as a V peak here. You can put as a hat, V with a hat, V peak, right? Okay. And next, converter 2. If converter 2 operates with a delay angle of alpha 1, the armature voltage will be constant. Alright, so the key there are actually a few modes also. We can also have this non-circulating current operation, non-circulating current, whereby what does it mean is that if you use a non-circulating current operation, you're going to have a the controller alpha here will operate. The converter 1 will operate while the converter 2 is shut off, completely shut off. So the firing angle, the circuit, the control circuit is quite complex circuit actually. So it will not trigger when converter 1 works. This is only for non-circulating current operation. Okay, so for quadrant 1 and quadrant 4, you're going to see that only alpha 1 is being supplied to the thyristor 1, thyristor 2, thyristor 3, and thyristor 4. However, converter 2 will receive no pulse at all. No pulse at all. Okay, so it completely shut off. So only converter 1 works. And when you operate during Q2 and Q3, then going to shut off converter 1. So this is completely shut off, and you operate with converter 2. Right? So current will flow in that direction, isn't it? Current will flow in that direction into that. Sorry. Different. Okay, so current will flow in that direction. Okay, negative current, and converter 2 will work based on the alpha. So that is non-circulating current. But in the case of circulating current, which means both converter will work. In this circulating current mode, it actually refers to the current in the output side here. So when the circulating current works, which means current still flow in that direction, and that also works in that direction. Okay, so there is a circulating current. Even though converter 1 operates, converter 2 also have some current flow, and therefore it also operates. So in that case, if you operate with a circulating current mode, you're going to have the firing angle whereby if alpha 1 is 90 degree, so at the same time you're going to have 90 degree for the alpha 2, which means 90 degree plus 90 degree will be equals to 180 degree. If you change to alpha 1 equals to uh, 30 degree, so what will be your the alpha 2? It will be equals to 150 degree. So in this case, you're going to see that the converter 1 will operate with a positive voltage here, right? Is that it? VT here, V out 1. If I'm going to write as a V out 1, will operate a positive, isn't it? Because we have this 0 alpha to 90 degree positive output, and if alpha is beyond that, going to have negative voltage, isn't it? So for if in this case converter 1 will have a positive output, but for the second converter here, it will experience a negative voltage. So initially you're going to have positive negative here, isn't it? V out 2 initially. But in the case of 150 degree, so the converter here will have a different polarity, isn't it? So it will also have a different polarity, and this is your V out 2. Right? So therefore, what does it mean? V out 1, the magnitude, if you look at the magnitude during 30 degree and 150 degree alpha 1, alpha 2 triggering firing angles here, you're going to have V out 1, the magnitude is equals to magnitude of voltage or the average voltage, sorry, the average voltage of alpha V out 1 will be equals to V out 2. Okay, so this is happens only for circulating current mode. Right, so this is preferable because the firing angle circuit, the controller circuit will be a lot easier or less complicated than the previous non-circulating current. Okay, so this is your voltage equation, and you must have this restriction. Yeah. Right. If I can show you the simulation, you can actually simulate with the, I can have this three phase. Okay, this is also to show you how the continuous current mode operation with the discontinuous current mode operation. You just simply have that output current. Okay, run the simulation. So your output voltage is negative, okay, because you have 150 degree operation, so you have negative voltage here, isn't it? So if I can go back to here, if I measure, then it will give a negative voltage. If I can show you, so you have a negative voltage here. VDC equals to 486.6.7 voltage. Okay. So negative voltage because it goes beyond 90 degree. The output is 90 degree. Okay. So I also have this simulation of dual converter. That you can try that, or you can do it individually just to understand. This is better, right? So I model this. Okay, if I can run that, look at that. This is converter 1. this is converter 2, and I have this current operate in that direction, and the current here operate in that direction here. Okay, if I run the simulation, what happens? Okay, so this is VDC, the output for the first converter, and if I can give you the output voltage for the second, and therefore this is the output voltage per second converter. Remove this, and I have Vy minus Vrad. Right? I should be the other way around. Sorry, there you are. Yeah, so you have, it follows this line to line voltage, and this is the VDC. If I can show you again, the voltage across that, positive and negative, and here I'm actually measure the positive and negative here, isn't it? So therefore, in this circuit you have 30 degree, for second converter is 150 degree, and that's why if you look at the circuit just now, it will give a negative voltage for converter number 2. It will give a negative voltage. If I can go back to here, look at that, this is negative voltage. But if you but V out, okay, V out is actually equals to negative V out 2, isn't it? It's the negative polarity of V out 2. We'll come back to the circuit again. Look at that. So if you combine here, okay, so this is, that we have V out 1 there, and this is plus minus V out 2, V out 1. So if you measure, if you refer to this, we're going to have VA, the voltage across here, is actually equals to V out 1 positive, or equals to negative V out 2, isn't it? It is negative because you measure from there to there. So your VA equals to negative of VO2, but it is equals to positive V out 1. And therefore, you don't have a, so therefore you operate under what? Quadrant 1, quadrant 1 operation. So you can have for all 4 quadrants operations by using this dual converter. Okay, clear? Right. So now we're going to continue with the next on the 3-phase voltage. Right. So for the 3-phase voltage, you can have a few circuit connection. The first one can be the half wave or midpoint converter, whereby you're going to use only 3 thyristors. I hope you still can remember. 1, 2, and 3 here, connected to your, so you have 1, 2, 3. Okay, connected to your R, L plus back EMF. Okay, back EMF. There. So this is a half wave or midpoint converter, and then we can also have the semi converter drive. Semi converter is that you arrange 6 devices, but the first half, the top group here is control rectifier, which the thyristors, but the bottom group will be left as the diode, be connected as the components that you use is actually the diode. So this is half control or semi converter 3-phase rectifier. Okay, so you only have the top group here is thyristor, the bottom group is diode. That will connect to again Okay, so we have a few here, and then if you can read, the armature circuit is connected to the output. Three-phase drives are used for high power application, definitely. Of course, larger than the single phase operation. So it can go up to megawatt power level. The armature current mostly continuous. It is mostly continuous. So you don't discuss on the discontinuous operation anymore. So it is a continuous current operation, and therefore the motor performance is better compared with the single phase drive. Similar to single three-phase drive, may be also be subdivided into that three-phase semiconductor, three-phase full converter drives, and three-phase dual converter. So we're going to focus on only these two: three-phase full converter drives as well as three-phase dual converter drives. Okay, and this is some of the I get this from the Boldia books. Right, it's best if you can find the Boldia book. Try to search for this book, and it will describe you and will give you this table, right? So for this single phase, half wave single phase, you can go up only to 0.5 kilowatt, which is 500 watt, and it is a first quadrant operation. If you have a the midpoint converter, the half wave converter, and it only can goes up to 50 kilowatt, and it is a two quadrant operation. You can have positive and negative. And next, if you have the single phase semi converter, a full wave converter with diode operation, so there is a diode here, freewheeling diode operation. In this case, you only have a first quadrant, one quadrant. That also goes with a semi converter. Look at that, this is semi converter, whereby you have the thyristor at the top group and diode on the bottom group, and you combine with a freewheeling diode. So if you combine with a freewheeling diode, you don't have the negative operation here. So no longer negative operation at the output. And this can go up to 100 kilowatt. Right? And next we have this full converter single phase. Full converter, it can go up to 50 kilowatt, and it's two quadrant operation. Three phase full converter operation goes to 1.5 megawatt, and you can only operate again two quadrant. But if you combine as the dual converter, so both here single phase and three phase dual converter, so you can operate with four quadrant operations, and it can goes up to 15 kilowatt, and that can be 1.5 megawatt operation. Okay, so with this circuit, the three-phase AC is converted to a DC using 6 switches. So you have 6 switches here, and and the output is connected to that inductance, and you have the triggering actual armature current, actual speed. So you have the reference. So this is the this is the reference maximum with desired current. So this is your reference. Okay, this is your reference parameter. This is a measured parameter. Okay, and that gives the firing angle for all your thyristors here. So it's always G1, G2, G3, G4, G5, G6 connection. The label of the thyristor here is very important. So it actually follows the sequence of operation. So you start with G1, then the next 60 degree will be G2, the next 60 degree will be G3, next 60 degree will be G4, next 60 degree will be G5, and finally G6 will operate in one cycle. Okay, so that's why it always arranged. If you open the book or any power electronic books or drive books, it's always addressed or labeled as G1, G2, G3, G4, G5, G6. So if you draw, you always have this label: G1, G3, G5, G2, G4, G6. Okay, I'm not going to go back to the power electronic subject. So this is already explained in the power electronic subject last semester. Okay, so next. Okay, some equation. if you consider the three-phase full AC drive, so you start at this point, isn't it? So this is always your reference, the 30 degree. This is where you start your alpha, isn't it? Alpha equals to 0 right at this angle, which is 30 degree from the 0 crossing of the red phase voltage here. So this is your red phase voltage, start to cross into the positive. So from there 0, from there to that alpha equals to 0 is 30 degree. The commutation angle, 30 degree is commutation angle, and that define where is alpha equals to 0. So alpha start from here, this is alpha equals to 0, and then if you increase further, for example, here you have alpha equals to 30 degree. From that point to that point is 30 degree. Right? So if you want to find what is the average value, you just put that into this equation and you will get the average value of the output here. So again, I can show you, I think I have shown you just now, you have two quadrant operation whereby you can have positive voltage output and you can have also negative output voltage there. So Q1, Q4, and your current always operate in that direction. Cannot operate in the opposite direction. Cannot operate in that direction, isn't it? So your thyristor will not operate if you have current flow in that direction. Will not be triggered if you have alpha current flow in that direction. Okay, so that's why you have a positive current here to that. Okay. This is the equation that you need to. I think this is from previous powertronic. You did the derivation. You can find the derivation if you 3V peak line to line over pi cos alpha, the RMS, and this is the peak value. Sorry, this is line to line voltage, and this is the phase voltage, and it is a peak value. It's not a not the RMS, but peak value. Be careful with that. It's a peak value. Sometimes written as V line to line M. V line to line M. The line to line peak voltage. Okay, that equation. Again, equation again. Okay, for dual converter operation, right? So we have this. I've shown you just now. So this is where you have the condition of alpha plus alpha 2 equals to 180 degree. Right? You always have to be alpha 1 plus alpha 2 equals to 180 degree. This come from the condition here. V out equals to V out 1, but it is equals to negative V out 2. So V out. So if you have negative V out 2, then you have the positive. Right? Yeah? This right. So what else? So that means if you have alpha equals to 30 degree, then look at that, reverse, isn't it? So here we have V out 1 positive, V out 2 will be negative. Okay, so it operates until 90 degree. Next, if you increase further alpha, now you're going to see V out is positive, V out 1 is negative, V out 2 is positive, V out 1 is negative. So this is very a good plot to show you what happens if you have alpha 1 and alpha 2 here. It's always reverse, isn't it? Which means if you stay at this particular point, so let's say this is 30 degree for alpha 1, but for the alpha 2 it is reverse. It is 180 degree minus 30 degree. So here you have 180 degree for 150 degree for alpha 2. Different angle, but if you add both together, we're going to have a 180 degree. So in this case, we have a positive voltage here but for V out is negative voltage, but if you look at the magnitude, it will be the same magnitude. So in that case, we have V out 1 operation. So again, Q1, Q4, Q2, Q3. Okay, that's for the three-phase or the AC controller. Okay, back to the continuous current operation. You can also refer to Sharkawi's book, page 172. Okay, to read further what is the continuous and discontinuous current operation. Okay, so come back to the three-phase full wave dual converters. So this is the equation that you need to memorize, and this from the Powertronic books, subject last semester. So the output can be defined by this equation: 3 multiplied by root 3 V phase peak. This is the peak value divided by or maximum value divided by pi cos alpha 1. And if alpha 1 equals to 0, then it gives you the V out max. So V out max equals to 3 multiplied by root 3 V phase over pi. Okay, and multiplied by cos alpha 1. So the maximum output voltage is due to alpha equals to 0, 0. Okay, so that VL1, VL2 based on the alpha 2, and this is the quadrant operation. You can operate at all 4 quadrants operation. Okay, so now we're going to continue with the chopper or DC to DC. So the input is DC, and then we have the output of the controlling the DC motor. Okay, so again you can work for first quadrant, second quadrant, and as well as a 4 quadrant circuits. Okay, so the first let's look at the input here. DC-DC converters are normally designed to provide output DC waveform at adjustable voltage level, so you can adjust the voltage so that you can control the speed. This converter also known as a choppers because you know that the DC voltage, the input DC voltage is always a constant, isn't it? So how you're going to change the level is by chopping. Chop an amount of time so that it goes to 0, right? And then you chop again so that you can have the average value can be different level of output voltage DC. So you can have a step down, or known as a buck converter, step up boost converter, and finally you can have a buck boost that can do both operation. You can step up or step down the output the input voltage. And next, in most electric drive application, the DC converter is a step down, so you use the buck converter. So we're going to look at the buck converter circuit and look at how the speed control can be done. So just again, this is again and again we're going to look into the 4 quadrant operation. If you have a torque versus speed, then it will be 1, 2, 3, 4. If you have speed against torque, then you have 1, 2, 3, 4. And this is again, and if you represent that in terms of voltage and current, you're going to have Q1. So this is always Q1, quadrant 1, quadrant 2, quadrant 3, quadrant 4. Right, so it's a voltage versus armature current. Next, all right, so this is the buck converter, and we have a separately excited again. So you have a different winding circuit for the field, and then we have the armature connected to this what we call it, 2 quadrant transistorized DC-DC converter, or known as a buck converter. So we are dealing with the buck converter, step down converter. So look at this. This is current, input current. The output current is the constant DC current, and then this is the input side. So now K is the duty ratio. Sometimes we represent this, label this as a D. T, isn't it? Duty ratio multiplied by the tip time. T is the period. The period for 1 cycle. So this T, the period. So this is the duty ratio. So K or D can be represented by value of 0 to 1, or sometimes it's in terms of percentage, 0 to 100%, right? Okay, so that is a we across this is the voltage across your uh, transistor here, switch. Okay, voltage across the switch, and it is only a first quadrant operation, right? So the current only flows in that direction, and you only have a positive voltage. Okay, and the voltage also can be only positive, right? Sorry, positive voltage across the terminals here. So VA is only positive, so it only can work on the quadrant 1. Okay? And this is a equation. I think it's a familiar equation for the buck converter. So output voltage VA equals to K multiplied by Vs, or sometimes we use D, then Vs. D is the duty ratio, or in terms of time you have T on time divided by the period T. So that gives you D or K. Right. The power supplied to the motor is the out equals to the average value VA, the VA multiplied by IA, and that also can be represented by supply voltage KVS IA. It's the average armature current of the motor, and it's ripple free. Assuming lossless circuit, so we have P in equals to P out. Therefore, VS IS equals to VAIA, and therefore you can get the output current equation. The current equation, it can be the IS, the supply volt current, equals to K multiplied by the IA, the armature or the output current. Some related equation, important equation. And then next, okay, so here you have this circuit, two quadrant transistorized DC-DC converter drive. So how you do it? You're going to connect another thyristor. You need to use another thyristor here. Put in this connection. So you have Q1, Q2. Q here is actually switch 1, switch 2. Sometimes labeled as Q or S1, S2. So you don't get confused with the quadrant Q1, Q2, right? So the S1 and S2. So here you have you need to consider a few conditions so that you can work with the quadrant 1 and quadrant 2. Okay, so the current can be in positive direction, or it can be negative direction, right? But if you look into the voltage, it can only have the positive voltage. It's always positive voltage, but current can be positive or negative. Two conditions of current can flow in the circuit, and therefore that makes these two quadrants rise to work on the Q1 and Q2. Okay, quadrant 1 and quadrant 2. Okay, so now you have to listen carefully how this is work. For quadrant 1, what you need to do is the power control. So remember, this is controllable, full controllable switches, which means you can control the turn on and off of the switch, which is cannot use transistor here. So you cannot use DHY, is not allowed in this circuit. You can use MOSFET, you can use BJT, you can use IGBT, which is controllable switches. And usually if you represent this, this is actually a MOSFET, isn't it? So MOSFET always have this anti-parallel diode connected across. I mean, this is a body diode, because body diode, or you can add another external diode, isn't it? But this diode, it's if you use a MOSFET, you is always there. But if you use a transistor, then you need to have an external diode connected in this direction. right? So how the circuit works, for let's consider a quadrant 1. Quadrant 1 whereby you have a positive voltage, positive voltage, and the current flows into that back EMF. So this is to consider the first quadrant 1 operation. So here you need so in this power control, because of power control or motoring mode, you have Q1 D2 operate. So only Q1 and D2 operate. Right. First, you consider Q1 on. Only Q1 is on. So this is you turn on Q1, and therefore this will appear as a short circuit, isn't it? So it will appear as a short circuit. Therefore, the current start to flow in that direction, flow in that direction, and flow in that direction. Goes through the armature winding here, resistor and inductance, and back EMF, and come back to your supply here, DC supply. And in this case, current start to develop, isn't it? So current start to rise, IA start to rises. And if you look further, VA equals to VS, isn't it? Because this is short circuit connected to altogether until the positive terminal. So VA equals to VS. Right? And next is when you turn off Q1 on Q1. Right? So therefore you can instruct your pulse to your Q1. So this here we have Q1 on, and here you have Q1 off. So during this time, let's have a look. So Q1 is off, isn't it? Q1 appear as an open circuit. This is open circuit. Look at that. So no current flows here. Still we have current flow in the output side, isn't it? Still IA flow in that direction. Therefore, it will go through D2. So IA will continue to flow in this loop, this circuit, and therefore current start to reduce because you have a positive negative voltage here, isn't it? That forces current to reduce. So that's why you have this decays or reduce, decay or reduce through D2. So in this state, still we have it working in quadrant 1, but now current start to reduce. Okay, so that is the quadrant 1 operation. And then we have this regenerative control mode or quadrant 2 operation. So how to get that regenerative control? You need to set Q2 and in this state Q2 D1 operate. So you're going to see that Q2 and D1 operates. Okay, so in this condition, remember this is quadrant 2, isn't it? So your current flow in the opposite direction. Right? So if you look further, this is the current flow in the opposite direction, and still you have a positive voltage across the terminals here, and current start flow in that direction. So let's see, Q2 D1 operate and Q1 turn off. Right. So in this state, you have Q2 on. So when you start to turn on Q2, so it will appear as a short circuit, isn't it? So Q1 is off, isn't it? So what does it mean? So current motor acts as generator, IA rises. So you're going to see that now current flow in that direction, isn't it? So current start to increase because you have now you have back EMF here operate as the we call it as a generator. So it will start to increase current IA. So that's why you have motor acts as generator. So you start to giving power or giving current to the circuit. IA rises through Q2 here. So it will break that direction IA. And the other state is still in quadrant 2. Q2 is off. Suddenly Q2 also off. So it appears an open circuit here. Open circuit, this is already off. Right? Q2 is off and current flow in still in that direction. Right? So how is it? It will go through D1, isn't it? So current IA will flow through D1 and give us back an energy to the supply Vs here. So that's why you have Q2 off. IA flow through D1. Look at that, D1 here. So it will select this path. Okay, D1 and energy returning back to the supply. So that is where you have the condition of regenerative control. Okay, so you can refer to Boldia page 95. Okay, if you have this book or you can find the PDF, look into the always if you see this, then you can refer to the Boldia books. So this is the book by Boldia, page 95. So you can refer to and look further. All right. So next is we have 4-quadrant transistorized DC-DC converter. So in this 4 quadrants, you're going to add another 2 transistor or MOSFET here, and therefore you can work for 4-quadrant operation. So voltage here, you can have a positive voltage as well as, if I can, negative voltage across that. Right? So you can tell or you can instruct the all switches here to work in certain manners so that you can have positive voltage or output negative voltage, and the current can flow both direction into the motor here. Right? So how the I will explain bit by bit. So let's consider Q1 quadrant 1 operation. So in this quadrant 1 operation, Q1 and Q2 will operate. Okay, so let's look further. Okay, right. So here the same explanation. So you start with quadrant 1 operation. So for quadrant 1 operation, you're going to see that the voltage is positive, isn't it? So you're going to see that positive voltage is positive negative here across the motor VA, and you're going to see that the current flow in that direction, isn't it? Current will flow in that direction IA into the motor here. So here you're going to let Q1 and Q2 to operate. Q3 and Q4 completely turn off. So Q3 and Q4 completely turn off, but Q1 Q2 you can control Q1 Q2 to operate. So remember, IA current flow in that direction. Okay, first let's analyze. So Q1 Q2 both on. So you start with Q1 and Q2 both on. So it will appear as a short circuit here, and therefore current will flow in that direction, flow into that direction and coming back to direction and goes to ground, straight from the supply voltage there. So, and you can see that Vs across VA. So if you measure that, it will equals to Vs, and current flow in that direction and current rises. Okay, so that's the first state. Next, you can have Q1 off. So you tell Q1 to off. Okay, this is off. Next, Q2 still on. So you still have Q1 on, and therefore which so current will flow in which circuit? So it will flow into the motor K, go to the Q2, and it will flow through D4, isn't it? So it will flow into D4 and it decays or reduce. Current will reduce because you have a positive negative back EMF here, isn't it? So that current, that voltage will oppose the current here, so that's why current reduce, but in that direction, still in that direction. So that is Q1 operation. Or alternatively, if you can also, if you don't want to follow that rules, you can also have the alternative whereby Q1 and Q2 completely off. So just now you have Q3 is off, Q4 is off, and Q1 off. you can also instruct Q2 off. And therefore, look at that. How is it going to do? So the current flow in that direction, isn't it? It is continuous current flow. Therefore, current will flow through D4, goes to this branch, to the motor, and come back to D3, and flow back to the supply voltage here. Isn't it? And that's why you have Q1, Q2 off. So IA decays through D3 and D4. So you will follow D4 and D3 here and go back to VS, and you're going to have a decay reduce direction. And next we have forward regeneration. So where is it? So forward regeneration is quadrant 2. Remember, you have omega or V here, or you can have torque, but it's current here. So this is Q1. Now you have Q2. So in this quadrant, you're going to see that the current is negative. So you are considering that direction of current, and you have the positive voltage across your VA. Great. So this is condition Q2, quadrant 1, 2. So in this quadrant, Q1, Q2, Q3 are off. So all Q1, Q2, Q3, Q1 off, Q2 off, and Q3 off. So Q4 on, first state, you're going to let Q4 on, okay, and the current start to rise through D4. Remember, we consider this current, right? So it will flow through, where is it? It will through current Q4 and D2. Is it? Oh, sorry for this. I should have cancelled that. Is it? So current will flow through Q4 and D2. Is it? In this case, you're going to have to see that rises, currents start to rise because you have a positive voltage, a negative back EMF here, and current flow in that direction. So current start to rise. Okay, so next you're going to have Q4 off. Remember, this is always Q3, Q1, Q2, Q3 are off, right? Current still flow in opposite direction here, IA, and then we still have positive voltage here, okay? But now Q4 off, so this is also, this Q4 also off. So what's it going? It's going to flow into direction D2 and D1 back to VS. Is that it? Yeah? In this state here. Okay, so current will flow through D1 and from the ground start D2, and it return energy through D1 and D2. So in this case, you still have current flow that direction, so it return back to the supply voltage, and VA equals positive voltage. So VA still equals to positive voltage. So this is two condition for forward regeneration, and I hope you can still follow. In quadrant 3, you're going to have Q3, Q4 operate. So this is how you're going to determine Q3, Q4, Q3 and Q4 operate, Q1 and Q2 off. So Q1 and Q2 completely off. So we start with Q3, Q4 on. So both are on, and reverse power control, quadrant 3. So is it? Current is negative, isn't it? Q1, Q2, Q3. So you still have current negative, so you are actually follow that current. Okay, so first Q3 and Q4 both on. So you turn on Q3, you turn on Q4. Therefore, and the voltage is negative, isn't it? So that is your VA, positive, negative now. Okay? Reverse, and therefore the current flow in that direction goes back to here, to there. Great. So it is known as a reverse power control, and a current rises in the reverse direction. And next, you're going to have the state of Q3 off. So Q1 completely off. This is off. Q1, Q2 completely off. Then you have Q3 off, Q4 still on. Q3 is off. Sorry. Q3 off, but Q4 still on. So the current still flow in that direction. How's it? So it will flow through D1. Isn't it? It will flow through D1. Wait. A falls through Q4 and D2. Yes. So current will flow through Q4 and QD2. So, and look at that. IA falls through Q4 and D2 here. Or alternatively, or you can also choose that Q3 and Q4 both off. So all transistors are off. All transistors are off. And then therefore IA decays through D1 and D2. So you can see that current here will flow through D1 and D2. Start from there, you will go through D2 in direction, go back to VS3. So that is quadrant 3 operation. Okay, I hope you can figure out quadrant. Oh, sorry, this is quadrant 4. Alright, this is quadrant 4 here. So in this quadrant 4, Q1, Q3, Q4 is all are off. All Q1, Q3, Q4 off. Then you need to let Q2 on. So current start to rises through Q2 and D4. So just follow my expression before and look at this statement. Q2 on, IA rises through D2. So Q2 on. So you just draw short circuit here. And current rises through Q2 and D4. So current D4. This is also separate. So, and remember Q4 you have a current in positive direction. So it will flow that direction. Right? So IA rises through Q2 and Q4. Remember the voltage is reverse, right? So the voltage is reverse, and that's why you also have to have negative back EMF here. Remember the 4 quadrant just now? That's why I keep on remind you of this. The best way is to refer to that quadrant. It's the best way to memorize everything because this the polarity of the back EMF also important for you to understand the current. Is it current rise or current reduce? Is it? So look at that. It's always follow the terminal voltage. So if you have terminal voltage have plus minus, so you also have plus minus there, and that one as well positive. If the voltage reverse, so the back EMF also reverse. The polarity there. This is how I'm going to memorize the voltage and current characteristic. So I'm going to continue again. Okay, and I also put into the circuits. Okay, to illustrate how the circuit works. Put this to repeat this statement, just to repeat that statement, right? And then I put it into figure. Then you can follow one by one my expression just now. So just so you apply the same understanding and try to. There's no easy way to understand a thing, isn't it? So you just follow the same. If you understand how the quadrant 1 works, then you apply for quadrant 2, quadrant 3, quadrant 4. Follow the same steps, right? Draw this, right? There's no simple way, easy way to understand all the materials here. So you have to do yourself, right? I just can show you one of them. All right, and next is the advantage of using switch mode converters. You can switch at high frequency, and therefore you can reduce the current ripple and increases control bandwidth, suitable for high performance applications. So that is how you go to control DC motor. And this is example taken from the books, Boldia books, right? 1 HP DC shunt motor is loaded by a constant torque of 10 Newton meter. So that will be your T here. Okay, the armature resistance of the motor is 5 ohm, and the field constant K flux equals to 2.5 volt. So remember, E always equals to K flux omega, torque equals to K flux I A. Great. So here it's tell me that the field constant K flux, so this here is 2.5 volt per second, but I don't really understand why the books the unit for the K flux volt per second. It should be, if you look for the K flux, actually equals to E over omega m, isn't it? And the unit should be voltage divided by radian per second. But here it only shows the volt per second. So here we have volt second per radian. So the radian here is gone. I don't know. I'm not sure why it is not displayed in this unit here. Okay, but we just follow the question. So you have a K flux 2.5. The motor is driven by a half wave SCR. This the half wave converter. And this is your motor, right? So you have half wave converter. The power source is 120 volt, 60 hertz. So this is American 120 volt, 60 hertz. The triggering angle alpha is 60 degree. Alpha equals to 60 degree. And the conduction period. So what is the conduction period? Is the gamma rate. And we know that gamma equals to beta minus alpha. So you can beta equals to gamma plus alpha. Right? Calculate the motor speed. You need to calculate what is the motor speed and develop power. Next, the solution is already there. Okay. So the average armature current is determined by the load torque and motor. So we have this equation, torque is equal to K flux I average. So it's already given to you. So I average equals to 4 amps. And this is equation taken from that slide, right? Vmax divided by 2 pi for half wave drive, half wave circuit. So we just follow that equation. We know that gamma equals to beta minus alpha. So we can calculate also beta here using that equation, and therefore that gives you this answer. Great. Because so that is beta here. This is conduction period. This is beta here. Right? So you just plug into the equation, and that gives you omega 16.22 radian per second. If you convert to RPM, you get the 154. Isn't it? So how to convert to n? 2 pi 60 over n, isn't it? 2 pi 60 over I can't remember. N equals to 2. N equals omega equals to 2 pi 60 over Allah. So you can you please and look for this equation, how to convert from radian seconds to RPM. I can't think. Omega is 2 pi n over 60. 2 pi n over 60. Okay, I get it. So omega equals 2 pi n over 60. So you can find n equals to 60 multiplied by omega divided by 2 pi. So that gives you the answer. The power developed, PD equals to EAI average, and that gives you this answer. Or you can have power equals to omega top, isn't it? You can use that equation as well. So you get 160. Okay, so you can this is 21% of the motor rating. Next example on okay. Now you still have the same problem, but now for the motor in, assume that the converter is a full wave type. So you just change the output voltage equation. You still have the same triggering angle, the conduction period is 150. So you just simply change the equation, and therefore that gives you that 246. And so now it increased the power. 56 pieces increase in power compared to the half wave. So half wave just now, you have the power of about, if you look, the power is about 162, but if you apply the full wave, then you get a power of 258.2. So it's a 56% increase in power as compared to the half wave. Okay, next. The speed of a separately excited DC motor is controlled by a single phase full wave converter. The field circuit here is also controlled by a full converter, and the field current is set to the maximum possible values. The field current is set to the maximum possible value. The AC supply voltage to the armature and field converter is one phase, 440 volts, 60 Hz. The armature resistance is RA 0.25. The current resistance is RF 175, and the motor voltage constant. Now the taken from different book, and the motor voltage constant is kV. Now use a kV, which is equal to 1.4 volt per ampere radian per second. So now let's have a look. What constant is this? The armature current corresponding to the load demand is 45 amp. The viscosity and no load are negligible. The inductances of the armature field circuit are sufficient to make the armature field continuous and ripple free. So this is a current continuous operation. If the delay angle of the armature is 60 degree and the armature current is 45, determine the torque developed by the motor. But B is the speed of the motor. So just let's have a look at how the kV is obtained. So you have this equation again. Okay, flux. Okay, and we know that flux is actually proportional to IF, and therefore you have K, KF, IF. Just replace that into that equation, and therefore it gives you that final equation. And therefore kV here, which is actually equals to K multiplied by KF, equals to E by KMF divided by field current multiplied by omega. So that's why it can give you the 1.4 volt per ampere radian per second. So in that unit. And that's the same equation, right? And therefore the solution is, there you are. You have this Vs, and then there's a maximum voltage here, or peak voltage, so you have to multiply by square root 2. This is RMS, so multiply by square root 2 to give you the maximum peak voltage. And this is the parameter. First you need to find the equation for Vf. The equation for Vf, which is that one, is it? This equation, separately excited. So you use a separately excited, and it is a full wave rectifier, and that gives you the maximum voltage across your output here. The voltage, the average voltage for the field winding. This is only for field winding. Come back to the solution, and therefore you can calculate for Vf, and then the field current is IF equals to Vf over Rf. That, and then the developed torque, use the equation just now, it gives you 142.4, and then you can find the armature voltage using the equation in previous just refer to that for the full wave, 2 over pi cos 60 degree. And for the back EMF, look at that, and give you 186.82, and from there you can find the speed, and the speed finally give you that figure here. Number 04 is for right. Okay, that's very much what is the DC motor control. We don't look into complicated circuits, just to give you just a taste, or to look into the basic DC drive control, DC drive, uh, by using the rectifier if the supply is AC, and you can have a DC-DC chop circuit where the input is DC and you want to control your DC motor, right? And so that's that's it, right? So if I have a example for again, I will share with you, inshallah. And all this will be available in your Google Drive, shared Google Drive. Okay, just download the notes and new notes. I add many things here, so just ignore the previous note on the DC drive, then just download the latest one, right? And next week we're going to continue with the control, the real control, where we're going to look at the closed loop control and the closed loop control of your motor. So it's going to involve a lot of Laplace transform, right? So inshallah we're going to look at that, and that will complete the DC motor drive control, right? Okay, until then, Assalamualaikum warahmatullahi wabarakatuh. Thank you.